right, let's get started. Thanks everyone for coming to the robotics seminar. It's our great pleasure to welcome Danfei from Georgia Tech today. He is a star in robot learning. He has many, many accomplishments. My favorite of which was his spectacular early career faculty talk at Coral, which blew everyone away. Russ Tedger came up to me and he was like, "Oh my God, that was the best talk I've seen in a while." So anyway, with those recommendations, I'm going to let him talk to us about his awesome work. We're very excited to have you. Thank you for coming.
You didn't mention the breakdancing.
That's right.
Oh, wow. No. Next year we'll do one for you.
Hell yeah.
Think about it. Well, what it should be.
Breakdancing 2.0.
Okay. All right. Everyone, thanks for being here. So very happy because this is actually the first time talking about this line of work anywhere. So you got a first peek of it. I made all the slides fresh. Also means that might be some bloopers. So I view this more like a kind of tutorial than a talk. So I'm gonna get into some details of the methods. So hopefully you can appreciate because I don't have too many flashy demos, but the ideas I think are quite nice. So let's get started. I'll call this problem task motion plan, generative task motion planning. So the main character of our story today is the Betty the Crow. Who have heard of Betty the Crow? Raise your hands. Cool, few people, right? So it's very famous. So Betty is a New Caledonian crow. She came to fame when back in 2002, researchers in Oxford discovered that she could actually bend little metal wires and twigs into hooks and get items to from the hard to reach places. What's remarkable is basically her ability to solve very complex physical puzzles, like the one shown in the video here. You can see that she's trying to kind of get stuff out of this like bottom tube, but couldn't. So she would like go and reach for some like hooks and try things and couldn't. So it will get progressively longer hooks from other tubes and eventually sort of solve this problem, right? So trust me, she will solve this problem, but know that the Betty has never been trained on this task, right? This is the first time that she saw this. She saw this problem, and so what happened? Did I break things? Oh, wrong button. Okay, all right. So fast forward 22 years later, robotics researchers have kind of created something that I think is equally impressive. We have managed to taught robots how to do highly dexterous tasks like solving Rubik's cubes or tie shoelaces. When I first saw this video from Google DeepMind, it immediately kind of reminded me of Betty the Crow because both show the level of sophisticated physical interaction that we thought were not possible for non-primate animals and for robots, right? But as trained robots, the difference between the surface level resemblance is also very clear. If you read the paper, you know that actually they train a robot for this exact task with more than 5,000 teleoperated demonstrations, probably takes a few months to collect and only works on the exact same exact task, right? If you change the table, it probably wouldn't work. So there's still a long way to go from what I call ultra specialized dexterity to physical problem solving intelligence that Betty showed, where she needs no data and can solve a complete downswing task by reasoning about complex constraints and just solve the problem. But then you may ask, what about LMs, VLMs, VLAs, all of these things, right? Did we say that I have common sense and can reason? Indeed, we have seen a lot of research on this, like where the models generate text that somewhat resembles like the logical process of reasoning, right? For example, ask DeepSeek here, is 1 + 1 = 2? And DeepSeek went on to, okay, so the question is whether 1 + 1 = 2. That seems pretty basic, right? But maybe I need to think deeper about it. So went on. Right? You get an idea. It's a bit too much overthinking. It resembles reasoning, right? And applied to robotics, we've seen works that turn a high-level command into more like fine-grained commands or even code-like structure shown here from Google DeepMind. The recent example came from a startup called Physical Intelligence. Chelsea even here tells a robot to make a sandwich with ham and cheese, and VLM then decomposed the task into like series of construction, like pick up the wheat bread and put on the chopping board and so on and so forth, right? What's amazing about this example is that this is unlike any of the robot planning work we're used to see, where there's a search or optimization algorithm that finds the best solution from a vast space of possible solution. The model here simply takes that instruction and generates a solution, right? Whether it's good or bad, it generates a solution. But clearly, we have not seen a Betty-like robot. So what's the catch here, right? So in my mind, the catch is best exemplified yet another video from Google here, right? Where Dorsar shows the one-take interaction with the Google Gemini robotics, right? So before this part, the robot shows some very impressive like instruction following behavior in real time, where Dorsar talks and then the robot does things like picking things, put in basket. But watch this.
If it is not a paper airplane, what did they just make?
Very quiet.
You made a paper boat. I made a paper boat. Can you pick up the paper boat and put that in a basket?
Notice that the robot did it before she even said that, right? It's a blooper, but I think it kind of says something deeper about the problem. The problem is that today's like reasoning model really is about behavior selection through language like interface than something grounded or more deep about understanding the physical constraints of a task so that it can be useful for robot learning. And there's only very surface level connection between the reasoning side and the acting side of robotics. And reasoning, the model only knows very, very little about the physical world to meaningfully solve this problem. Well, luckily as a field, we have spent decades trying to solve this problem and connecting reasoning and acting, right? One of the most general frameworks called task motion planning, or TAMP, where it solves a complex problem by jointly search or optimize for a high-level task plan and synthesize low-level control. Typically, TAMP problems are like arranging objects on tabletop here, but occasionally people like Mark Trisson would come out and say, TAMP is more powerful than that. I can actually solve very complex problems like taking a hook and like to reach the hook and to get to keep, right? Like the things that the pro could do. One nice way to conceptualize TAMP is through a specific extension called multimodal motion planning. And the modes here are essentially these thin manifold, like these green sheets and purple sheets represent a small set of states with smooth transition dynamics, right? Like moving through free space or like sliding on a smooth surface. TAMP is to plan a sequence of modes and low-level control commands that can transition through these modes to reach a specific goal. In a way, what enables TAMP to solve these complex problems and generalize to new one is two things. One, bi-level communication. The chosen mode sequence affects the feasibility and optimality of the underlying control command, right? You have to kind of simultaneously optimize at both levels, which modes to connect together and what are the level of control commands that can reach a goal. And also, very importantly, compositional generalization, right? Modes and their controllers can be combinatorially combined to solve a large space of problem, and that resembles some sort of combinatorial space. So while TAMP is very powerful in general, it is not without problem. For example, the work I showed you, right, like the hook using example where robot is able to kind of solve very complex problem. We need a differentiable physics engine to begin with, and painstakingly writing down all the possible modes that we need to do, all the constraints on the equations as constraints, and to do a very massive search problem. And a mid-sized problem like the one I showed before takes anywhere between 3 to 5 minutes to solve, which is quite expensive. So while we have a computational framework that gets us close to the physical problem-solving intelligence like Betty the Crow, it is not very practical and for solving real-world robotics problems. So let's zoom out and compare these two paradigms, right? And through a few questions, like computational efficiency. Does hardware problems take longer to solve? Does the model actually learn, or does it require specific domain-specific knowledge? Does it solve complex physical problems, and does it generalize to new ones, right? So for TAMP, we know that it's a search or optimization program, so it takes longer to solve bigger problems. It requires domain-specific knowledge. It's not necessarily a bad thing, but you have to write down rules and things for each specific problem you care to solve. It is very powerful to solve constraint optimization problems, and it does compositional generalize to new problems. For foundation models, it is almost constant time. I know it's arguable. I mean, there's GPUs powering all of this, but you can I guess think of it as a constant time, right? So it might extend based on length of the solution, but still it's a pretty impressive feat. More data is better. I don't have to explain this, and very little evidence that can solve very hard physical problems. And in order to generate a new problem, you have to do a lot of prompt engineering. So for people who have worked with LLMs, you should be familiar with this kind of back and forth and try to kind of sort an answer out of a foundation model, right? So what I want to talk about today, right, finally get to the point, is a different kind of paradigm, that what I call generative task motion planning, or generative TAMP, where the key idea is to pose TAMP really as a fully generative problem, where similar to foundation models, we can simply generate a solution from a distribution instead of doing search. The components are almost all data-driven, so more data equals better. And we use techniques from planning as inference to solve tasks with complex constraints. And most importantly, we'll be able to achieve compositional generalization by composing learned generative models together to solve new problems. So that's sort of the goal we want to aim for, right? Generative TAMP. So, and it's still a work in progress, so I'll put it two words on the title. But I'm going to kind of talk about a body of work from our group. Generative skill training, generative factor training, and CompDiffuser, or called generative skill or generative trajectory stitching, right? So it's like generative models plus some sort of way to combine them together to solve a complex problem. And at the end, I'll conclude by looping back on the topic of foundation models and share more of my thoughts on what's missing and whether robots should think in English, right? So let's start by the first word, generative skill training. Any questions so far? I want to kind of make this a bit more interactive. I treat this more like a lecture or a tutorial. Yeah. Okay. All right. Awesome.
You're so good at lecturing. That makes a lot of sense.
Thank you so much. All right, so let's start with general models for planning, right? So it's a general domain where just like images and music, we can train models to generate plans. So typically you start with a bunch of trajectory data like human demonstrations, then train a conditional general model, so P, tau, and C, where conditional C may include context, goals, constraints, and so on and so forth, and tau is basically output plan, right? And then at test time, you take samples from that distribution, and that's your solution, right? For example, you can generate short trajectory like diffusion policies on top, whole motion planning trajectory in the middle, or entire videos on the bottom, right? So this is actually a video synthesized by a video generation model as a form of sort of quote unquote plans, right? So if you're interested in knowing more about this field, we actually have a nice survey paper on this, and you can just go look, but that's besides the point here. So there's a survey paper. But they're not perfect, right? Like most methods built on deep neural networks, they are data hungry. We can make two observations. The deep learning magic is some sort of interpolation and limited extrapolation in a latent space learned from data with dense coverage. And second observation is that what makes planning problem very hard is the long planning horizon and many constraints you have to satisfy to solve a problem. And consider this sort of likely landscape of sort of something that model learns, right? And an ideal solution landscape, like ideal what it is that some smooth landscape where you can just interpolate amount of things you've seen, right? Like that red dot is a valid plan somehow, right? But in reality, you have two challenges, right? First, long horizon data are hard to collect. So you're unlikely to have achieved coverage, density enough coverage to solve the problem. And second, the real planning solution, because of all the constraints you have, is very likely something like on the bottom, which is like very jagged, right? So interpolation is not unlikely to give you some valid plan. It's something in between, right? And with many constraints like this, and it's very hard to solve. So in a way, our goal really for this work is to want our planners to systematically generalize to new problems and possibly sparse data, and allow enforcing some sort of constraints like goals at test time so that I can satisfy all the things we want to plan to solve, right? So the question is, how do we do this? Recall what we said for TAMP, right? The key to compositional generalization, which is a form of sort of generalizing with finite amount of knowledge is there sort of the key is that they have modes and sort of transition controllers that can be composed to solve new problems in planning. And if we view is from a sort of a probabilistic generative model lens, modes can be basically viewed as distributions of short behaviors or skills, and plans are joint distributions of a long sequence of mode distributions, right? So it's the joints of all the modes. And through this lens, we want to see if we can enable generative planners to achieve test time composition generalization and constraint satisfaction by combining these modes together. And by enabling this, we're hoping basically to make TAMP a fully generative problem. So we're going to take step by step. It's not going to be fully generative for now, but later we'll see some version that it becomes something of a fully generative problem, right? So let's see how we can make multimodal motion planning problems a generative problem. Right, so to start with, we sort of equate modes with some sort of transition dynamics pi of k, where it's basically the pi of k basically captures the precondition distribution 0 and effect distribution. So what is the required condition or states that the skill is going to be successful, and also what's the outcome of that, and so the parameters that bridges in between, right? The actions or the grasping codes or the whole motion trajectory for that particular skill. So yeah, the parameters can be anything, right? It can be anything that specifies how the skill should work. And the transition amount of modes is finding the distribution of this intermediate states that S1 that satisfies both the effect of the pi 0 and the precondition of pi 1, right? So that's chaining two modes together. And it can further generalize this to like k different modes. And the planning is basically given a task skeleton of like, we know which kind of modes should be connected together, what is the joint distribution of the entire plan, right? So for now, we assume task plans given, later we'll try to relax that constraint. Okay. Everything clear? Good, all right, awesome. So there are two remarks I can make. One is that mode distributions only require short horizon data to learn because they're skills, right? You don't need like 1,000-step data to train these kind of literal skills. So you can train these skills with very short horizon data. And mode distributions are local and go agnostic, meaning that you don't have to, we can basically treat this as little building blocks, and these can be reassembled to solve different problems. So that's how we will be able to achieve composition generalization. But deriving the joint plan distribution is as hard as solving TAMP problem itself, right? It's not like we're making this probabilistic makes it easier. It's actually a pretty hard problem. So if you think about this problem where, sorry, let me just replay this. The problem about this is that the red cube is initially out of reach, so you have to use the hook to get the cube so that you can put the cube on the table, right? It's a kind of a simple problem that also needs to reason about tool use and reachability and all kind of things, right? Let me just play this video again. So yeah, so you get ideas of sort of what the robot has to do in order to solve this problem. So we actually to solve this problem, you have to resolve a multi-step dependency where step 4, which is this pick red box, really the feasibility of doing that really depends on how you pick up the hook, right? Sorry, the hook is pick up, not rack is pick up, right? So if you grasp the middle part or the wrong end of the hook, you will not be able to use the hook to actually to get that cube correctly, right? So that skill parameter in that state actually determines further down in the future what's your feasibility of your plan, right? So in other words, we need some ways to sort of propagate information among these modes in arbitrarily long chains. So let's work this out by looking at sort of to compose these two-step distribution using models pi 0 and pi 1 through what we call forward-backward chaining. In standard control, we use forward chaining, right? So we'll just basically roll out the dynamics and sort of linking the first fields and the second through their sort of shared transition state S1. And this ensures that S1 is actually works both as an effect of pi 0 and precondition of pi 1, right? But forward training alone is actually myopic, short-sighted, actually only cares about sort of, is this transition feasible? And as was mentioned, the model needs to generate states based on some future constraints. So we need some ways to propagate information backwards. How we do this is actually quite simple. You just simply consider the backward dynamics, right? So consider if you let's say you start with some states that already satisfies the precondition of pi1. You want to see basically what kind of transition, backward transition would pi0 allow, right? So it's kind of propagate information backwards. Okay, now we kind of have some formulation to propagate information both directions. We need some ways to sort of go beyond just one step, right? We want to propagate beyond, to multiple steps and arbitrary long chains. So intuitively, we need something that's kind of iterative, right? So because if you have a two-step, one-step kind of propagation algorithm, you want to iteratively propagate throughout a chain. And we want to do that with a general model. You might have a guess, right? What algorithm we should use, which is denoising diffusion, right? If you are familiar with denoising diffusion, you know it's an iterative algorithm where you try to sort of denoise some noise source like a Gaussian back to some real data samples, right? I'm just going to do a really quick primer here for those of you who are not familiar with diffusion. So what we want is some arbitrary data distribution p theta x, theta being the neural network parameters. And what we train neural models to learn is not the distribution itself, but the gradient of the log likelihood, or what we call score function, right? So it's the gradient of the log likelihood of that particular sample at some particular denoising step, right? And the iterative denoising is basically iteratively predicting what noise actually causes this noisy data and try to backtrack it, or other words, you directly subtract the gradient of the log likelihood from it, right? So to make it more likely to be more in distribution. And if you kind of plot this in a 2D domain, something like this, right? So you start with a noisy data, right, on the right, and you go backwards to some clean ones, and you can see that these are basically vector fields, like pointing to directions that will make them more likely, right? So diffusion model. One other very interesting property of diffusion models, it is very, very flexible. You can basically compose arbitrary distributions together by adding their score functions together. So let's say you have this joint distribution and would do this conditional decomposition just by moving the sort of the conditions back down to the bottom. You could actually treat these as three separate distributions, and each of them is a denoising function or a score function, and each of them is a diffusion model. You can train three separate models and combine them to generate this joint distribution. Right? It's math, right? It's Bayes rules. It's nothing kind of. What's nice thing about this is really we're treating sort of generation problem as a gradient descent problem, right? Where you can contribute gradient from different models. Right? That's the key idea. So back to our problem formulation, we now want to basically take this and put that into denoising diffusion, which is actually very easy because you can just add diffusion score functions together. The epsilon pi0 and epsilon pi1 being the learned the score function for these two separate skills, right? We don't have to train them together. They can be learned totally separately. And there's this marginal term on the right. I'm going to explain it a bit later, but you can see that this is a very nice way to combine different distributions together to jointly sample something that satisfies the sort of the mutual variables, right? Is that clear? Yes.
One quick question I missed. So at this point, are you assuming this pi sequence is given?
Yes. Which modes connect to which other modes is given. That's what we're assuming. But we don't know what the modes, each of these modes are trained. They are diffusion models, basically. Yeah. I'm going to talk about how we can relax constraints a bit later in the third work. I'm not going to relax constraints here. Yeah. Okay. Hopefully this is clear. Good. Again, this is a sort of a lecture, so I'm going to get to very specific things here. Yeah. So the marginal term actually turns out. I mean, if you know, probably knows that it basically offsets the sort of the how likely it is for each of these directions, right? So if you make this more negative, it means that you're trying to sort of push in the information in the other direction. So what you end up doing is linearly combine these two terms, right? So you can set a gamma, and the gamma basically decides use the marginal to as a way to tune the information flow backward and forward. And depending on sort of how strong how big that denoising score function is, information will go to different directions, right? So So this is hyperparameter continuum. I'm going to show the fact of doing that a bit later.
Are you inspired by like CFG?
It's exactly CFG. Yeah. So it's just, the derivation is exactly as classifier-free guidance. Yeah. It's just math works differently. Yeah. Yeah. Okay. So now another thing we can do is enforce time constraints, where we can just impose arbitrary constraint like h tau on there. It can be anything as long as it can be even non-differentiable if you want. And we can do the same trick, right? It's just the summation of the gradients, log likelihood gradients. And typically what we do is just like put an exponentially short terms on there to make any arbitrary cost function like a energy function, right? So it can be anything. For example, we can make a continuous cost function. And for example, to maximize the distance between all the cubes, sort of the classical TAMP problem of type packing or type placing, right? They should not be in collision, so we want to push them outwards so that they are not in collision when you place on them, on that tight surface. And you can also specify a very specific state you want to reach by kind of specifying a delta function, right? So that can also be turned into an energy function as part of the optimization process. So that's how you satisfy any constraints you can pose that test now. Okay, all right. Yes.
Yeah, I have one question.
Yeah.
So I'm assuming they're like basically each model trying to capture the conditional distribution of
Yeah.
like a state transition.
Yeah.
Skill.
Yeah.
I wonder how to compare against like learning a single model for all skills, and we can implement that model as a convolutional neural network with a kernel size of 2. Then like basically as the CNN go over the sequence, it's basically checking the feasibility for each transition. Yeah.
You could implement that way. It's exactly the same thing. Like it's just a more efficient way of implementing this. I'm going to show you like putting everything together. It's basically exactly what you said, except that like the denoising diffusion, you have to do the multiple steps, right? You can implement this in one massive unit. Yes, it is possible. Yeah.
Yeah, I guess like maybe like do you have any thoughts on like which way of like this implementation is like better, like a single model for all skills or like a different...
Single model? Well, there are two different versions of this, right? Like single model for all of the skill, but each skill, the model still can only capture like one skill at a time, right? It's like you have a conditional skill model, or you have a single model for all of the long horizon data altogether. Which one are you talking about?
Maybe a long horizon one.
Okay, then you have to have long horizon data.
Yeah, I guess that people are, some people like diffuser, you can
Right.
yeah, both different trajectories.
Right, exactly. So there are two different perspectives of compositional generalization. One is that it's like if you expose part of the computational space, you can generalize to the rest of the computational space. What we're trying to do here is zero shot, right? We only have the components, we can connect them together to form the entire space, right? So that's the difference. Yeah.
Is your diffusion model autoregressive model going for like one state to next state, or is it like a...
It's parallel. Everything's okay. I'm just going to show this here, right? So what happens is that given some start states, calling skeleton modes, we're going to take a sample of the entire plant, like just like a vector, a single vector that represents the entire plant, right? Length K plant, and we're just going to do this, like we'll in-paint the individual states, and in parallel, predict the noise through basically connecting the mutual variables together, right? Through the marginals, and then impose some constraints, and all of this diffusion model together will, in parallel, generate the next step, right? Everything happens in parallel. So we don't do autoregressive, because if you think about linear combining score functions, there's no dependencies. There's no sequential dependencies on it, right? It's just everything can happen at the same time.
But the model itself actually sees one time step.
Yes.
Exactly.
Yeah.
Two time steps.
Well, yeah. The intersections basically.
I see.
Yeah. Okay. All right. So now you just go on to do your thing, right? And generates in chart plot. Okay. Is that?
The states and actions here are like geometric values.
Yeah. Right now we're going to assume a low dimensional state space. I'm going to show a version of this, doing video generation with this model. Yeah. We make no assumptions about state and action, so it can be any arbitrary thing.
So you multiply two probabilities.
Yeah.
Only when they're independent of each other.
Well, if you discount their marginals.
The question is, if your model is trained with some condition, then
Yeah.
you have your constraints.
Yeah.
I feel like you can
Yeah.
sort of assume that, but in a way, the constraint is going to change in the nature. I mean, you're leveraging.
Yes. So yeah, none of this is exact, right? So we're basically putting everything together in the same massive denoising process, and hopefully that gives us the correct answer, right? There's if you like make assumptions about conditional independence and how this constraint, this H will affect all of these distributions, that will change, well, that might affect the optimality of the solution, but under this sort of data-driven approach, we have found that this is super effective in terms of solving the problem.
So given that understanding,
Mm.
what kind of tasks this model works well? What kind of tasks this really is trouble because it's poor assumption?
Right. I can talk a little bit about this after finishing discussing this work, right? Okay. So I'm going to show you some quick results. So what you're about to see is all of the tasks share the exact same 4 skills: pick, place, push, and pull. So like we're trying to just one set of model and solve all of the tasks. I'm going to show you both sim and sim real. So one of this task is basically you have to kind of push this blue block into under the rack. So you have to kind of move things out of the way first, and then use a hook to push things in there. So, right, so we can basically solve this problem in one go. It's actually pretty reliable. You solve this problem like 60 or 70% success rate.
When you're learning the pick, place, push, pull, are you learning it per object, or are you just learning it?
So that's a good question. So right now, I think this is learned as a general model, like for every single skill, and depending on the idea of that object, it will adjust basically distribution, generative distribution. It's still like a tiny conditional distribution there. Yeah. But none of this is kind of a problem in the sense that later we're going to show that we're going to use a single general model to learn everything. Yeah. Okay. All right. So yeah, this is using the tool twice to solve the problem, where you have to like put a cube, aim it so that you can push it in there. Right. So all of this is solved at test time. The model only has these 4 skills at its disposal, right? Like and then everything is basically resolved. The specific parameters and all that are generative testing. Yeah.
How do you specify the task?
It's in here. This is the delta function, the version of constraint when I talk about the delta function. The top, lower bottom.
Bottom right.
Bottom right, sorry, my brain is not working. You could also do in painting. You can do anything. Like there are many different ways to specify a sample that this constraint needs to generate, basically. Yeah.
So you treat the goal as a constraint.
Exactly. Yeah. Pretty much. Right. Yeah.
So is the state and action are then the parameters for those learned skill models?
What are the skill parameters? All right.
Are those like the state S and A?
Yeah.
Are they parameters of those learned skills?
So states are just like gigantic vector of every single thing in this environment, right? Action is like, it can be anything in this here where we use parameter skills. You can also just use that motion. Like you can directly generate entire trajectory if you want. Yeah. Okay. All right. So
You said they're parameterized skills.
Yeah.
What does that mean?
parameter means that there's a controller, a written controller that takes in a single set of vector that says pick a specific continuous parameter, and it will just go execute this motion parameterized by this continuous vector.
Got it. What is that continuous vector?
Pick pose,
Pose?
approaching angle, or these kind of like semantically meaningful variables, not trajectories in this work.
Okay.
Yes. Okay. All right. Cool. All right. So one thing I want to also mention is that this gamma parameter can actually change the behavior of the model. For example, If you only consider backward only, it will try to satisfy the constraint by imagining steps that could have led to that, but it's actually not consistent with the forward dynamics, the dynamics of the physical environments. So you can see here that it just kind of imagined itself picking up the hook, but it's actually not picking up the hook, right? And between these two states, a lot of objects change places, right? So it's basically generates something affected by the combined score function that is not satisfying the forward dynamics. And if you only consider forward dynamics, all of the steps are satisfies forward dynamics of the environment, but it will just do random things. For example, we'll pick up a cube and place it down, pick up a cube and place it down, right? So it doesn't actually do useful things. And if you sort of achieve balance, if you just set a gamma to half and half, it will basically kind of reliably solve the problem. So that's kind of how you interpret this variable, right? And we can also specify test some constraints, like for example, the one I showed here, right? Like is maximize distance amount of placed blocks. You can basically reliably achieve this problem by providing additional cue about how to solve this problem, right? For example, this original goal is to set all of the cube to have certain within this bounds, right? The cost function is that these cubes should be within the bound of this this table surface. But if you further suggest that, okay, you should place them to maximum distance to each other, you can actually achieve much better performance by just providing this additional score function guidance. Okay, and finally, we show that we could actually sort of do some replanning, for example, excuse exposure. So just kind of mess with the system, and it will just try to still do the task, because the distribution that these objects fall into requires certain steps to be done through forward and backward chaining. Yeah.
Is there a reason why it always goes back to the same initial state?
Yeah, it's just implementation of the skill. Yeah, so that you can detect the QR code or the A4 tag. Yeah. Okay. All right. So let me summarize this work. So we can pose TAMP problems as a generative model problem, barring the task planning part. And sample planning level distribution, we can do this by forward and backward chaining. And chaining is basically linearly combining score functions and iterative noise in parallel. And we can control the conditional information flow back and forward and impose arbitrary test time constraint through that formulation. And we can solve basic long horizon planning problems without long horizon data. So that's the takeaway for this work. Is there any other questions for this? Yeah.
Yeah, quick question. So,
yeah.
After you train the model and generate the chain for the same task,
yeah,
or the same constraint, have you observed like any influence from the initial noise of your sample or generation that will influence your final?
Yeah. So there's a chance where it will generate wrong output, right? Like, well, I mean, you can think of this as sort of a gradient descent problem, right? Depending on initialization, we end up with at different places. It will definitely affects. It's not like every single time it will be successful, right? So it does, but if you kind of just think of that as a gradient descent, like clear space, this is what happens.
So do you think like if we're thinking from like the inverse problem, do you think like the final samples are all from the posterior distribution based on your constraint?
Yeah, pretty much. Yep.
So question about specifying the constraints.
Yeah.
So when you said that there were constraints that were the delta function,
yeah,
that's like implemented through the in-painting? Is that?
Oh, no, you can do either. Like the initial state is specified through in-painting. The goal is specified through delta function.
Okay.
Yeah.
And then the second question. So if you had a constraint that's, for example, with the blocks, for whatever reason, let's say you had a specific order in which you wanted to pick up the block.
Yeah.
How would you specify?
So this is all done through task planning, right? We are not controlling the order, the task sequencing of these modes. I'm going to talk about a way to do this without that, but like this is how we resolve that, okay, like the ordering of the task. Yeah. We have basically we assume task planning is solved in this work. Yeah. Cool. All right. 18 minutes left. Went through first work. All right. Bad idea to do this in a lecture, but okay. At least I think most of you understood what a method is, right? So, okay. One important question for this is that iterative denoising by propagating information through neighboring chunks neighboring modes is actually a bad idea if you think about how many steps, denoising steps you have to do in order to propagate the information like to arbitrary steps, right? So, so if you think about this, this is sort of just like, it's a dumb algorithm, right? If you think about it. So what if we could actually add additional pathways to this graph, to this chain? Right, and if you just kind of redraw this thing, it looks a bit more familiar. If you add squares, it becomes even more familiar, right? Some of you might already know there's a factor graph, right? It's actually like a specialized version of factor graph. So the second work is generative factor chaining, where actually kind of generalizes this thing to a factor graph and do message passing through denoising diffusion on a factor graph. So hopefully, once you already understood the specialized case, the generalized case, I'm not going to go too much details. So we can just kind of rewrite this equation in a very compact form. The top is a joint, bottom is marginal. And if you think of that as a factor graph, the top is the factor distribution, the bottom is basically the marginals for the specific variables that has outgoing and incoming factors, or like unit factors or binary factors, right? So this turns out to be like a known algorithm back in early 2000, and it's called beta approximation of the generalized belief propagation. And so the approximation is exact when you have acyclic graph. So in this case, since we don't have directionality, it is somewhat of the exact. But once you put into score functions, it becomes sort of a denoising diffusion process. So that's sort of a connection to the specialized case. So what we are essentially trying to do here is to embed modular diffusion models as learned factors and denoising as generalized message pass. And kind of math just works out. Right? So,
why not just train like one joint distribution model?
Because you don't have the joint distribution data to train a joint distribution model. That's modular. Exactly. You can train individual bits and pieces and put them together, test them. That's the essence of this. Yeah. Okay. All right. So So I'm going to quickly explain why TAMP problems can be treated as factor graphs. That's actually known results from if you read the task motion planning survey paper, they actually have a nice diagram of explaining why TAMP problems can be treated as factor graph. For example, here, this kind of free space motion, it can be thought about as like, do not collide into things while achieving go from Q0 to Q1, Q being the configuration of the robots, and the graphs being forming a stable forming kinematic constraints between the gripper and objects through this specific graph G2, right? So that's like, you can think of TAMP problems as factor graph problems. So the difference here is that we're, again, going to do denoising diffusion on this. And we have a very specific design choice to make this even more generalizable. For example, we're going to further factorize state space, right? We're not going to treat this state as a single unit vector. We're going to treat individual object-centric features or poses or specific aspect of robots like gripper pose or orientations, right? And we'll go treat the temporal and spatial factor constraints separately. So the temporal constraints being the sort of basically the skill transitions dynamics on a subset of space. For example, if you pick up something, the transition will only care about that specific object and specific arm, right? If you were talking about multi arm manipulation problems, for example, here we'll say that going from left to right is temporal. And this orange box is basically the temporal factor that connects what's before and what's after, and the parameters, the skill parameters for that skill. And spatial constraints can be thought about as things that are happening sort of at the same time. For example, what's grasped stays grasped when you do this free space motion. Right? That's one way to specify the constraints. And you can generalize this to solving by manual manipulation pretty easily, because now, even if you only have single arm skills, you can actually put them together in a factor graph and generate a consistent solution. Right? For example, here you have left arm, right arm, and hammer in a box. Actually, no, there's no box, actually. Ignore this. Right? So what it does is that it basically says, okay, these things should be grasped, but like basically both arms should grasp this thing at the end of the handover. right? That's just one step thing. And you have different separate skills for each of these arms. Then you can generate a consistent solution at the end of this denoising process. So what it looks like is that sort of, for example, you have like one spatial constraint, you can generate a bunch of like stable grasping poses. If you have like temporal constraints, which is a skill, you can generate things that are sort of move while holding an object. And you have bimanual or two things to compose together, you would generate things like this, right? For example. So spatial temporal vector. This is just a tiny bit of like a gigantic graph, right? Is that clear? Cool, awesome, right? So yeah, we can basically solve, for example, multi-arm manipulation problem with only single skill models, right? By just laying them into this vector graph. So we're going to do problems like pick up, like do handover. Sorry, the video is a bit slow, so I'm going to speed this up a little bit. So I'm just going to, yeah, so you get an idea. Just put this into the box, right? Or you can do things like hammer nail, where you have to hand over the hammer first, and then hold this nail down and hammer. So all of these parameters are generated by the model. All right, so one thing you can observe is that there are many different ways to mate two skills together, right? Like there, for example, handover, you can kind of do all kind of different configuration that satisfies these spatial constraints. So what it looks like is that, for example, it actually generates different distribution for different eventual goals. For example, for hammer place, where you just simply hand over this hammer, it can be any configuration, right? So it's a more flat distribution of the handover, like the grasp and regrasp sort of parameters. But for hammer nail, it's actually a very bimodal distribution. So because you have to satisfy certain constraints so that you can hold one end of the hammer and sort of hammer it, right? So you can see here that we only have two ways to hand over this for hammer nail, because you have to satisfy all the collision constraints and also be able to hold the end of the hammer in order to do the hammering motion. Right? So I'm going to skip this part because sort of you can also swap out the skeleton order. It still works because now we have the direct connections on the graph instead of a linear chain. And we can do some other tasks like sort of pour things. Just go speed this up a little bit, right? And do things like that. And also like coordinated sort of reorientation of a pot so that the actual trajectory generated is sort of, it's consistent, right? So it doesn't actually cause wacky things to happen. Right?
So how difficult is it to design the constraints? Because it seems like it's pretty direct. The constraint space is like in the same as the the generated space.
It is. So yeah, everything's in a surface explicit state space. You can write cost function. You can write anything you want, basically, and add that as part of your score function. Right? So it can be anything.
Like you need to.
You can write it. You need to write it. Yeah. So you can also learn it. You can learn a classifier to do this classifier-based guidance. Right? It can be anything. And yeah, we can also like do some wacky things like it will try to pick up this orientation with these two graphs. But actually, unfortunately, this gripper has different frictions in sim and real, so it will kind of drop the pot if you try to do this, like the specific grasps. Anyways, so that's a super quick overview of the generative factor chaining. And
Slightly dumb question.
Yeah.
How are you?
No, there's no dumb question.
Training this.
How do I train this?
Yeah. Are you using human demonstration?
No, actually, all of these are basically scripted. Like this is sort of an algorithm framework. So we didn't actually go all the way into real human data and everything, right? So we actually generate this data with scripted policy, and some of them are generated with reinforcement learning policies, so that we can show that it works. Right? Yeah. Okay. So we specifically designed some skills so that I can generate data, meaningful data to show the frame. Yes.
Yeah. Okay, and then like how do those training data differ from the demos that you're showing us? Are they similar?
The demos? Oh, they're
Just like the objects rearranged slightly.
yeah. So they're just different ways to grasp object. There's a very diverse set of grasps for a single object, basically. So the question is, how do you kind of join these diverse distributions together to solve so that they satisfy the constraints for the entire plan? Yeah.
Just to clarify, you are given the pathway graph, right?
I was given the header. Yes. Again, we're assuming task planning is solved. Yes. You're right. So I'm going to talk in the third work about how to relax those constraints. But okay, I'm going to stop taking questions and just rush through the third work. All right. So you get a takeaway, right? So the obvious missing piece is we're not doing task planning, right? So it's just all we're doing is like laying out the factors or the modes and see how they can be connected together. So yeah, we're assuming basically task skeleton or a factor graph symbolic structure is given. So we're basically essentially telling the task algorithm which distributions should be joined together to provide a valid solution. So the question is, can we still achieve test time and composition generalization without a task plan, right? Because I mean, the essence of TAMP really is a high-level planner that tells you how to put things together so that you can generate a valid solution, right? So the how to put things together part, if that's gone, can we still solve the problem? So the last work I'm going to talk about really quickly is okay, I'm just going to rush through this, but the essence is that we're going to train a single diffusion model for all of the skills, but not as long horizon, but still short horizon data. But we're going to generalize this. Instead of having the subscript pi k, now this is just one diffusion model that generates all of the things, right? It can be picking, placing, navigating through a narrow corridor, anything, right? But this short horizon. And our goal is still chain together k trajectories to solve a long horizon problem. No task planning, just chain, right? So things, example is like navigating through a maze, right? So we actually have some short horizon navigation trajectories, and the question is, can we generate long horizon navigation trajectories? The idea is simple, but the challenge is actually pretty interesting in the sense that if without task plan and with a unified chunk distribution, what will end up happening is that you have like kind of a continuum of things instead of individual modes, right? And what happens is that if you try to kind of denoise 3 identical diffusion models to generate a consistent plan together, ideally what happens is this, right? They kind of self-rearrange themselves so that they generate something that's consistent. But in reality, what happens is that it can be any order, right? Like any diffusion model can generate any part of the solution, which means that it's actually a very hard mode searching problem in this denoising process. So it makes it very challenging. The second problem is a bit more subtle in the sense that the math we did with averaging score function is actually not so great when you have many constraints, because that's one failure mode I'm going to talk about, is that if you have something that tells you average 2 vectors together to go to a correct direction, what is going to happen is that if you have a weird distribution, it's going to fall in between 2 likely answers, right? For example, it will do something like this, right? It's not a likely solution, but still satisfies the tail and head constraints. So that happens all the time if you actually kind of train a unified model for everything, because the search space is simply too big, right? So in between solutions is a challenge. So what we came up with is a different way to just go chaining. Essentially, what we're doing is, instead of just averaging score functions, what we're doing is noisy sample conditioning. 4 minutes. So I'm going to, essence is a different way to decompose this distribution. Basically, neighboring chunks determines the center chunks. And so what it looks like is that we are going to start with 3 noisy chunks at 100 steps, which is the denoising step. What it does is that it will take out the overlapping region and the center chunk and condition the generation with the sort of the overlapping chunk instead of averaging their score function. So it's a conditional generation problem. It will look at something that's noisy, but something that's like going towards a certain direction. I will say, okay, I should be consistent with these noisy samples. So this is how my sample should look like, right? It's kind of roughly what. So you will do this in parallel. and it will be able to basically generate consistent solutions result. So it's a very simple change of how we do message passing. So there are different ways to do the sampling. The one I showed you is parallel sampling. You can also do autoregressive sampling, which is slightly better, but it's very subtle, where basically denoise one thing to a slightly better future timestamps and use that and the lagging behind sample chunk to jointly denoise the one next to it. So it's an autoregressive process. It actually produces a better sample, but it's a lot slower, right? So what it happens is that instead of averaging, what it's going to do is to produce something that's likely and tries the best to satisfy constraint. It may or may not satisfy constraint, but at least the sample that's generated, it is likely because we're not actually averaging score functions, right? Okay, so some quick results. So we can compose different number of chunks to solve these maze problems. For example, this is k equals 5. If you have a more complex problem like k equals 9, you can form a very, very long chain from these small trajectories. And if you compare with GSC, you can see that actually in the middle part, like this part actually penetrates through the wall because it does score function averaging, right? In our cases, we don't. It slightly generates some like disconnect point trajectories, but in most cases it's fine. And if you just train a single unified diffusion model, this is denoising this is decision diffuser, it actually just interpolates the whole thing. Right? Results. You can also think about look at different number of chunks for the same problem. You can see that at k equals 11, it actually does a lot of back force motion to consume the unused chunks, but it still generates something reasonable. Okay?
So what happens when you delegate the model?
It will just have missing pieces. Yeah. All right. Okay. All right. 1 minute. Okay. So I'm gonna show some other things like. You can actually directly plan a high dimensional problem. This is 26 dimension, and also like compose locomotion and kicking soccer together, and also compose kicking soccer, locomotion, maze navigation together. Everything's possible. Right? It's not perfect, but it still works, and you can do humanoids, like ultra high dimensional planning. It still works. It's not perfect, so it just does some wacky things because the source data is not good. It's reinforcement learning that generate data. Okay, so I'm going to quickly show you something. Can I take 2 more minutes? Yeah. Just standing here is very daunting.
I know.
Right? So the promise of like deep general models is that you can work on high dimensional data, right? For example, diffusion policy works on image data. So the question is, can we actually just project these things into some learned latent space and still do chaining, right? It turns out we can. We just take some tokenizer, NVIDIA tokenizer. This is Cosmos tokenizer from NVIDIA, and just do this. It just works. It's a 3-step assembly problem and 400 steps long. It chains together and generates a video. It's valid. You can just roll it out. It works. Right? So, I mean, although like whatever I showed you before, all trajectory loaded data, it works on high dimensional models. Okay. And also can satisfy arbitrary constraints with guarantee is actually very hard. So we can sometimes the constraint actually push you out of the likelihood region. So we are working on some ways to like merging optimal control and denoising diffusion to satisfy safety constraints. Right. Finally, 2 minutes. I'm going to do a very quick discussion about foundation models, reasoning, and should robot think in English. So despite what we said about foundation model earlier, one thing we cannot deny is that they're very, very powerful, right? They have a lot of common sense. There's like a ginormous latent space that contains all of the things, including some solutions for that particular problem that Betty Crow is able to solve, right? At the same time, it also contains knowledge about things that Betty Crow would never be able to understand, like placing a wooden spoon on a pot of boiling water prevents it from boiling over, and stock market manipulation has serious legal consequences, right? But as we know, most of this knowledge is semantic, and to harness this knowledge, one needs to build a system around largely semantic knowledge system. So the answer is, should robot think English? And the answer is no. probably know, but why, right? So as recent work of my student, when she did kind of shed some light on this, so what we're trying to do is basically doing behavior cloning with human data, right? Like human egocentric view data. And what we're trying to do is just predict what's going to happen next, right? What the person is going to do next. And turns out that it's actually a very hard problem because some of these failure cases is very weird in the sense that, for example, we see person cooking and they just look at their watch or look at the wall, right? For no reason. There's no way you can explain that from just that particular visual observation. Because we have such a vast space of goals and beliefs and constraints and space representation, that happens in the latent part of our brain, or our brain that we don't even talk to ourselves about it in English, right? So there's no possible data that can possibly teach model this kind of reasoning process, this latent physical reasoning process with just explicit reasoning traces, right? There's no way to do that. So my argument is that there's a very, very big unknown of in the middle, but I think it's very, very important to achieve both the physical problem solving technique, the internet scale knowledge, and tying shoelaces. And whatever is here, we don't know. We're starting looking at this problem. Is going to be very, very important for the next generation robot foundation models that can do all of these three things together. Okay, with that, I thank my sponsors and students. Ukarsh did most of the work, and Yunhao is considering joining Michigan. So yes, thank you.